Welcome, everyone. Thank you for coming. I'm Varun. I'm a Ph.D. candidate in ECE. My advisor is Professor Bill Sanders, and my committee members are Professor Carl Gunter, Professor Pete Sauer, Professor Clara Naste, and Professor Ravi Iyer. My topic today is data-driven methods to improve resource utilization, fraud detection, and cyber resilience in smart grids. Let's start with a quick review of smart grids. Smart grids are electric power grids that can be efficiently managed through data sharing between operators and consumers, illustrated on the left of the figure, and generators, illustrated on the right of the figure. Smart grids come with three consequences: good, bad, and the ugly. The good consequence is that because of increased connectivity and data sharing, resource utilization can be improved. There are other good consequences, like you can have improved efficiency and improved fault diagnostics. The bad consequence is that this data can be compromised by both consumers and generators for fraudulent monetary gains. The ugly consequence is that increased connectivity to critical controls increases the risk of cyber attack-induced power outages. Now, electric power is so important to society. It supports other critical infrastructures. It's important to our daily lives. And it's such a vital resource that protecting the grid from cyber attacks is a top national security priority. My PhD research addresses all three of the good, bad, and the ugly consequences of smart grids through $3 billion topics: resource utilization, fraud detection, and cyber resilience. So let's motivate these topics.
Is each one a $1 billion topic, and there are three of them?
I'm going to talk about...
each one a $3 billion topic?
Each one is multiple billion, and there are three of them.
Okay.
Yeah.
Just wanted to be sure.
Yeah. So let's first talk about resource utilization. So wind power, just as a case study, is being underutilized all over the world. In China, 21% of wind power is curtailed. And what that means is 1 in every 5 wind turbines is not being utilized. And that is because wind power is unpredictable, and so providers commit less power than they actually generate, and that difference is curtailed. This is better because this is a conservative approach, because the alternative would be to commit more power and generate less, but that would be a resilience issue, so they don't want to be doing that. Even so, the wasted potential is in the order of $1 billion every year. So the problem is that clean energy resources are not being fully utilized because their availability is unpredictable. And we're going to quantify and reduce that prediction uncertainty in the context of demand response as a resource in the context of commercial buildings, and wind power generation as a resource in the context of generation. Next, let's talk about fraud detection. In India alone, electricity theft losses amount to multiple billions of dollars annually. And in developed countries like Canada, utilities, like in this case BC Hydro, are using smart meters to detect electricity theft. But that approach is not sufficient because smart meters have been shown to be, they have vulnerabilities, and these vulnerabilities have been shown that they can be compromised. So this is still an open problem. And to address this problem, we're going to identify different types of meter fraud and use data-driven methods to mitigate them in the context of commercial and residential buildings on the consumption side, and solar and wind generation on the generation side. Finally, let's talk about cyber resilience. And our study focuses on generation controls. In 2007, researchers at the Idaho National Labs, in their own simulation testbed, showed that a cyber attacker could enter generation controls and cause serious damage. In fact, they blew up one of their own generators. In 2009, malware called Stuxnet entered uranium centrifuges in Iran and managed to damage those facilities. More recently, in 2016, crash override caused a blackout in the capital city of Ukraine by cyber attacks on grid control systems. So the problem that we are addressing is that there's an increased risk of generator compromise because of increased connectivity that's coming with smart grids. And the cost is in several billions of dollars For example, Enron in 2001 triggered several power outages in order to drive up the prices and make huge profits. And that was $40 billion impact on just California. So my work will study the impact of these attack parameters so that concrete steps can be taken to mitigate them in the context of generators with turbine controls, such as nuclear, thermal, hydro, and wind. My thesis contributions address resource utilization, fraud detection, and cyber resilience in the context of both generators and consumers. First, we will show how we can reduce wind power prediction uncertainty. We will show that demand reduction potential can be increased. We will show that solar generation fraud as well as consumption fraud can be mitigated, and we'll show approaches by which all of this can be accomplished. And finally, we will discover, analyze, and empirically detect a new attack that we discovered that can cause power outages through attacks on generation controls. Through these contributions, we will demonstrate that empirical models of generation and consumption constructed using machine learning and statistical methods improve resource utilization, fraud detection, and cyber resilience in smart grids. So let's talk about empirical models. Inherently, these models are realistic because they're based on real data, and that's the main advantage. But there's a requirement that data must be available in the first place in order to use empirical models. And not only that, you need computing resources and also storage resources in order to process this data. Now, because these requirements were not met in the 1980s and early 90s, researchers in that area preferred theoretical models, stochastic state-based models, and that was, in fact, the topic of my advisor's thesis. The limitation of empirical models is that the models may be too specific to one particular system. And so we may ask ourselves, if the model does not generalize, can the approach apply to other systems as well? And I say yes, they can apply to other systems as long as those systems' data have the same characteristics. Now, based on the request of my committee, I'm going to be talking about my thought process in applying empirical models to smart grid data. I'm going to be addressing the thesis topics, the three topics, using data from consumption in buildings, solar power generation, and wind power generation. So let's talk about the characteristics of this data. First, let's look at consumption in buildings. Consumption in buildings tends to be very repetitive, and there are so I've shown on this slide 3 ways by which the repetitive patterns can be captured. The first is the existence of low-rank approximations. And what that means is that the data repeats in a linearly dependent fashion. The second is stationary. That means that the distribution of the data does not change over time. Then you've got seasonality. Now, solar power generation also has this seasonal behavior. But solar power generation also benefits from strong spatial relationships. That means that if your solar power is being inhibited by cloud cover, so there's a cloud over your house, then chances are the cloud is also over your neighbor's house. And so you can look at that correlation between the neighbors. Now, for each of these characteristics, there is an appropriate modeling approach. And the appropriate modeling approaches here are by no means comprehensive, but they were, for the most part, designed specifically for these data characteristics. Now, the important aspect of this work is that the framework applies to any type of data set. So if you are not doing research on smart grids, you could still use this framework on your own data by first asking yourself, what characteristics do your data have? So if your data have any of these characteristics, then you could still use the same modeling approaches. So now let's start by talking about resource utilization. So here, the billion-dollar problem is that clean energy resources are being underutilized. And the problem exists because the availability of these resources is difficult to predict. The objective of this research is to improve utilization of these unpredictable clean energy resources. And today, we will talk about, very briefly, how that is going to be done in the context of wind power prediction uncertainty. I'm going to summarize this research in just one slide because my committee has seen this research before, and I don't want to be repeating what they've seen. So here, the objective is to maximize the utilization of wind power through better prediction of future wind power availability. The challenge here is in trying to find ways to reduce the uncertainty associated with these wind power predictions, and we solve that challenge by not only using historic data, but also additional data coming from fine-grained weather forecasting engines. So if you just use historic data, the models are called autoregressive or AR models, or nonlinear autoregressive or NAR models. And if you use those models coupled with data coming from other sources, then it becomes an AR model or an NAR model with exogenous inputs. So that really was the difference between our work and related work. We evaluated our work on a data set of 21 wind turbines in Vermont, and we showed that we were able to reduce the width of the confidence interval of prediction errors by 20%. So let's talk about why that's important. If you were to take just a very simple example over here, and in this example, in related work, if you were to measure the width of your confidence interval of prediction errors, let's say that was 100 megawatts. Then in this case, if you were to use this approach and you wanted a 99% reliability of commitment, then you would, let's say, for example, be able to commit only 10 megawatts of wind power. But if you use our approach, because we are able to reduce the width of that confidence interval by 20%, then in this case, we were able to double that commitment. And the importance of this is that when you reduce that uncertainty by reducing the width of these confidence intervals, more energy can be committed with the same reliability, and resource utilization can be improved and curtailments reduced. So now let's move on to the next topic, fraud detection. Here, the billion-dollar problem is that meter fraud can lead to billions of dollars of losses for electric utilities annually. The problem exists because of inadequate security. Analog meters can be tampered with, and smart meters can be compromised for cyber methods. And one of my committee members was interested in talking about how we could prevent these attacks. And you could prevent these attacks by patching the vulnerabilities in the meters. But the challenge here is that these vulnerabilities already exist in hundreds of millions of meters that have been deployed. And there is no practical way to patch those vulnerabilities because there is no secure mechanism in place to roll out updates automatically over the network. So here the research objective is to detect and mitigate meter fraud committed by malicious consumers and generators. And again, today I'll talk about it from the consumption perspective. Yes?
You're talking about tampering with the meters.
Yes.
Bypassing the meter altogether?
Yeah, so in India, that is what is happening. So in India, they're just completely bypassing the meter. So my work addresses both bypassing the meter as well as tampering with the meter.
So it's kind of like a tampered meter instead rerouted.
Right, exactly. Exactly.
A meter that reports zero or something.
Yeah, and I'll talk about the ways by which that reporting can be done. So here the threat model is as follows. The attacker is an electricity consumer, and the defender is the electric utility. So if you look at the example at the bottom of the slide, here the consumer is consuming 50 kilowatt hours worth of power, but the consumer has either tampered with their meter or they've compromised their meters such that they are going to report to the utility that they have actually consumed only 30 kilowatts of power. So in doing so, they reduce their electricity bill by 20 kilowatt hours worth of electricity. The detection approaches that we have proposed use the data-driven framework that I had presented earlier in my talk. We're going to leverage the fact that consumption readings repeat in a linearly dependent fashion, and that is what the low-rank approximation means. And we will detect fraud using principal component analysis. And we'll also be leveraging the fact that this data tends to be stationary, so the distribution does not change over time. And we're going to use callback library divergence. So today I'm going to just talk about those two detectors, and I'm going to be presenting some new work in this area. We evaluated the detectors using a real smart meter data set from Ireland. And so this data contains 74 weeks of consumption at a half-hour time granularity. I'm looking at a subset of that data set, 500 consumers. So what we're asking ourselves in doing the evaluation is how much money can be gained through meter fraud. And the way we're going to do this is, first, we're going to explore ways by which we can circumvent detectors that were proposed in related work. A detector in related work is called this min-average detector. So we're going to look at that detector specifically, and we're going to look at how that works and what the worst case would be. The min-average detector is a very simple detector. The utility computes the averages of each consumer's readings over weeks in the past. So every week has one average. and then you compute the minimum of those averages in the past. And if your new set of readings has an average that's less than that past minimum, then you flag that as being anomalous. The worst case, so when we evaluated the worst case scenario against this detector, we found that on average, a consumer could steal about $26 of electricity per week. Now, it's easy to implement this worst case attack because all the consumer needs is their own consumption data. They don't need anything from the utility. They can just be monitoring their own data, and they can compute the average themselves, and they can inject readings for which the average is equal to their mean average from the past. So let's do a quick cost analysis of what that would come down to. So if you had about $26 per consumer per week, then that would amount to over $1,300 per consumer per year. And if you had 100 million consumers in your country and 1% were committing fraud, that is already a $1 billion problem. Our detectors, and I'll talk about how they work, the PCA-DB scan detector and the KL divergence detector, are able to significantly mitigate that fraud. In fact, the KL divergence detector mitigates that fraud by 96%. So now let's look at some new stuff. What I'd shown you on the right was still the same. We're circumventing detectors proposed related work. But on the left, what we're going to do, based on a request from my committee, is we're going to be looking at the worst case scenarios for the detectors that we have proposed. So that's like the adversarial example. So first, let's describe how these detectors work. So on the slide, I've got a chart, which is really a heat map. It is a matrix representation of consumption readings for one consumer. There are 60 rows corresponding to 60 weeks of consumption, and there are 336 columns corresponding to different half-hour periods in the week. The colors indicate the normalized consumption values, and what you can see with these green bands is that the diurnal patterns are very obvious. So you can see the Monday, Tuesday, and you can see the weekdays when the consumption goes up during the day, and then it goes back down during the night. And on weekends, you don't see those bands because for this particular consumer, they were not working on weekends. They're not as hard as we CSL students work. So, and so in this case, principal component analysis is an appropriate approach because there is a very visible low-rank approximation. So let's talk about how that works. So if you were to represent the original vector, so let's denote that with x. And we're going to project that into 2 dimensions just for illustration today using this projection matrix V. And in the low dimension, it becomes, you have 60 weeks, and each week, instead of being represented by 336 points for half-hour readings, it's going to be represented by 2 points. So in the low dimensional space, those weeks, each week is represented by 1 point. What you can see immediately is that most of these weeks tend to be densely clustered in that 2-dimensional space. And for that reason, we're going to use a density-based clustering algorithm. In this algorithm, if you look at the blue points, the blue circles, dots, those are called core weeks, and they represent the most typical consumption behaviors. And the anomalies are really behaviors that differ from these core weeks. And the way to detect those anomalies is there's a parameter which measures the distance of the points from the core weeks. So what you can see over here is that there's a non-convex boundary, but the non-convex boundary is really a union of circles. You're just looking at overlapping circles. So that region has overlapping circles, each of which are centered at the core weeks. And as long as your other points are within that region, they are not considered to be anomalous, but they're outside that region, they would be considered to be anomalous. And the radius of that circle is a parameter of the algorithm, epsilon, and I'll talk about that. So now we're going to look at some new work. New work for my committee that explores how we can best circumvent that detector as an attacker. The worst case scenario for the detector is the best case scenario for the attacker. And so we're going to formulate this as an optimization problem. And it turns out that this is a convex optimization problem. So let's talk about that problem. The objective here for the attacker is to create a set of these consumption readings that DA star sub A. And that is expressed by using the product of the reported readings at each time with the price of the reported readings, and then you multiply that with that delta T, which converts the power readings into energy readings. And so in this case, that expression, the objective, is literally the attacker's bill. That's the bill that they're going to receive for the T periods of consumption. The constraints are the detector constraints. The first two constraints are very simple upper and lower bounds. So the first constraint is just a non-negativity bound. Your consumption readings should not be negative. The second constraint can just be upper bounded by the maximum reading that you've seen in the past. The third constraint is the most important for our work, and that encodes the whole PCA DB scan detector. So what you see in this constraint is the first expression is the projection of the attack vector in the low dimension space, and I've circled it with the blue circle over there. So that red cross is the solution to this optimal attack, and you can see that that lies on the detection boundary. So that's where we are maximizing the attacker's gains or minimizing the bills. The second expression, the D prime sub n, that refers to each of the core points in that plot. And essentially what we're doing is we're looking at the distance between the attacker's point and the core point, and we're using the L2 norm as a distance metric. And because the L2 norm is convex, this whole problem boils down to being a convex problem. We want to ensure that that distance is less than the radius, that's epsilon, and that's the radius of each of those overlapping circles. So now let's look at what that optimal attack would look in the higher dimensional space. In the higher dimensional space, the point in 2 readings goes back to a point in 336 with 336 readings, so that's a full week of consumption. The red dotted line is the optimal attack.
Varun,
Yes?
you might have said it, and I may have missed it. What's the definition of an optimal attack, and who decides that it is optimal? I thought it's supposed to prove something is optimal.
Here you can construct the optimal attack. So the proof would be a proof by construction. So optimal means the attacker is going to gain as much as they can while circumventing the detector.
So you show in your thesis that this is the worst case attack?
Yes, so this is the worst case attack because it encodes the detector constraints. That is a constraint of the optimization problem. And the objective is for the attacker to minimize their bill. So it's optimal by construction. So the objective, as you said, is looking at it from the attacker's point of view. So this is the attacker's optimal attack. And that, by just looking at it the other way, is the worst case scenario for the detector.
So any other attack that I pick, you can show that the attacker would not
Gain as much.
gain as much.
Yes, correct.
Is that, and you prove that?
It's by construction.
Because he solves the optimization.
And that's you find the optimum by
Correct.
solving it?
Correct. Exactly. Carl.
Assuming that the attacker knows all of the data and the algorithm.
Yes, excellent point. So there are detection parameters. That's epsilon is one of the detector parameters. Then V, which is being used to project the data into the lower dimensional space, that's a detector parameter. And then we also need to know the set of those core points, that's another detector parameter. So in this case, the attacker will only achieve the optimal attack if they had full knowledge of the detector. And I mean, really, this is a theoretical result based on your request that that you wanted to see what is the worst case that can happen. So this is worst case in theory. So now let's look at another detector, and we will obtain the worst case scenario for this detector as well. That's a lot more complex than the one before. So this detector uses Kullback-Leibler divergence. And Kullback-Leibler divergence is just a very simple metric that measures the difference between two distributions based on their histograms. So here we've got 2 histograms. One is the histogram of malicious readings in 1 week, and the other is the histogram of my training set. So here I'm assuming that the data is non-malicious data. So what we're going to do is we're going to look at each of the bins. So that parameter B is the set of bins that are being used to create this histogram. And we're going to substitute the values into the KL divergence formula. So it's fairly simple. You look at the probability in each bin, and you compute the formula based on those probabilities, and you sum them over all the bins, and you get the metric. So in this case, that ki value works out to be 0.73. So why does that matter? If you looked at legitimate readings in 1 week, then you would see that the distribution is a lot similar to the reference distribution that we had. And so that ki value is going to be a lot smaller. So we can use that ki value for anomaly detection. So the way that would work is you would calculate ki between 1 week and in the test set and the full training set, which is so you compute ki with respect to the training set. And then if ki is greater than a certain threshold, you claim that this is going to be anomalous. So the way you could set that threshold is that you can compute ki for known legitimate weeks in your training set, and then you could set a threshold based on percentiles. So in this case, as you pointed out, the parameters are that tau and the bins that we're going to be choosing. And so for the worst case scenario, the attacker would need to know these two parameters. So let's look at the worst case scenario. Now formulating this attack was way more challenging than before, because the objective function, which is the same as before, we're minimizing the attacker's electricity bill, and the constraints, which are looking at these probabilities, they're seemingly unrelated. They have different variables. And so I was stuck on this problem for a bit, and then I figured out how to do this, and I'll show you how. So for now, let's just assume there's flat rate pricing. And we can extend these results for varying pricing, but that's just, there's a lot of messy math, so today I'm just going to, for simplicity, show you flat rate pricing. So this equation, we just take that lambda out because that becomes a constant. That's what flat rate pricing means. And so this sum becomes equivalent to the mean, reducing the mean of those consumption readings. And that is super important, because now that we've shown that minimizing the attacker's bill is equal to minimizing the mean of those reported readings, then we can express that mean as an expectation. And so now that we've got the expectation, the objective function and the detector constraints are all using the same variables. And so now we can solve this problem effectively. So there are two steps in generating the optimal attack here. The first step is we're going to derive the optimal distribution of these points. And then the second step is once we have the optimal distribution, we're going to generate our readings from that optimal distribution. So let's illustrate what's going on here. And here again, the KL divergence constraint is convex, and so this becomes a convex optimization problem. So let's illustrate the attack. So what you can see over here is the attacker's distribution of readings and the training distribution of readings. The attacker, and the way I like to think about it, is that you've got bins for the histogram, and what the attacker is doing is that they're taking sand out of the bins corresponding to larger readings and putting that sand into the smaller bins corresponding to smaller readings, so centered at 10 going down to something centered at 2.5. And in doing so, they are reducing the mean of the readings, because now the buckets corresponding to the smaller readings have more sand compared to the buckets corresponding to larger readings. But they need to do this in a way that circumvents the KL divergence detector, which is given with that threshold. So we can solve this problem, and we can find so here this P star sub A is the probability or the relative frequency of each bucket. So that's a vector of relative frequencies of each bucket. So once you've got this distribution, we can generate the optimal attack. So in this case, the optimal attack here is you're just injecting a lot of zeros, and then somewhere you're going to be injecting some larger readings corresponding to the larger buckets. So all these zeros over here correspond to well, they're not zero, they're small readings. 0 is the bottom of the curve, but yeah, that 2.5 or whatever corresponds to the readings here in this 2.5 bucket, and the larger readings correspond to the buckets corresponding to the larger values. And here I'm assuming flat rate pricing, but this whole argument can be extended to varying pricing. So let's look at the bottom line. The bottom line is that the worst case scenario against the detector's proposed related work do not perform, I mean, they're not too different from the worst case scenarios of our own detectors. So if you look at how much an attacker can gain, they'd only gain slightly less than what they would have gained from the detectors in related work. But as Carl pointed out, in the case of related work, it is very easy to compute that worst case attack because all you need is your own readings and you can circumvent the detector. But for our detectors, it is difficult to compute that worst-case attack because you need to have some insider knowledge at the utility. You need to know those detector parameters, and only then can you circumvent the attack. So therein lies the advantage. So let's summarize what we've talked about in fraud detection. So we quantified that an attacker can gain over $1,300 per year, and that leads to billions of dollars of loss for utilities. The KL divergence detector can mitigate fraud based on in comparison with related work by 96%. And we show that the worst-case attacker for PCA, DB-scan, KL divergence are hard for an attacker to implement because they need this insider knowledge and they need to solve. Then you need a convex optimization solver. So it's tricky to do that. What we haven't yet talked about, and I'll just go over it briefly, is that fraud may be committed by consumers with rooftop solar. So in this case, they're called prosumers because they're producing electricity through the rooftop solar, and they're also consuming electricity. And so Carl suggested a very nice way by which we could quantify these attacks. And that is based on how much time it would take to recover solar installation costs. Rakesh.
Very interesting discussions. I was thinking about analogous work that is being implemented when it comes to tax fraud detection.
Okay.
And there are two questions that come up in context of tax fraud detection that I think apply here too.
Okay.
One, what is an acceptable false positive rate? So
Right.
in case of tax frauds, for example, so it's easy to mark a tax statement as possibly fraudulent.
Right.
But if you do it too often, then the follow-through that's needed is so expensive that it's not worth for the government to do the follow-through on each of these statements that are marked as fraudulent. So you
Correct.
have a really low false positive rate. So I guess my first question is, what's an acceptable false positive rate for a work like this? Because it doesn't matter how much you reduce, from my perspective, it doesn't matter how much you reduce the improve the fraud detection rate. You don't meet that threshold of the false positive rate. There may be practicality challenges.
Right.
Second one is again analogy with tax fraud detection. There are high worth individuals and then there's everybody else.
Right.
And how important is it to make fraud detection harder for the common folks if it is easy for or if you can put in enough effort as a high worth individual to essentially commit the fraud. So analogy lies here as well. That yes, in terms of average statistics, you may have increase the difficulty of committing fraud.
Right.
But if it's still possible for an intelligent entity to commit fraud, then any high worth individual may still commit that fraud.
Right. Thank you for the question. So let me just back up a little bit. So I have in a very small footnote over here that all of these detectors, the detector thresholds, was set based on the false positive rate that I would see in my training data. So all of these detectors were set for a 7% false positive rate. And so that's why it's a fair comparison when I'm doing the comparison between these worst case scenarios, because that's how I'm setting those detector parameters. So now let's talk about first. So in my case, I'm assuming that 7% is acceptable. But let me talk about what the ground reality is. And one of the benefits of the way I've spent my time in graduate school is that Professor Sanders has been very encouraging of me doing summer internships. And so this summer, I was doing fraud detection for electricity consumers at a company, one of like a Fortune 100 company, energy company. And in my work, they were looking at a really good precision. Precision is true positive by true positive rate by false positive. For them was like 40%. That was really good. So if you can get something like 40% using all these data-driven methods, their client was paying the company millions of dollars to just get that. So you can get a sense for where that false positive rate must be. And 7 is definitely a small false positive rate to be looking at precision of something like 40%. The second point that you brought up was exactly my task in my internship. So up until I joined, they had a detection mechanism for detecting meter fraud, and their mechanism was being applied to all consumers. And so my task was to look at the big cases, the large cases. And so I made a separate detector for those large cases. And clearly, because you've got now 2 detectors, they become more suitable for their data set. So now my detector for the large cases is able to detect fraud in those large cases better than it was when it was trained over the entire set. It just, you're training over, it becomes more specialized, right? Now, it is extremely important to detect these large cases. In fact, let me tell you how it's done. So through these detectors, you can come up with a score of how likely this consumer is of committing fraud. And let's say that score is normalized and it goes from 0 to 1. Now let's say that there's a consumer who had a suspicious score of 90%. So you think with 90% chance this guy is suspicious, he must be committing fraud. And then you've got another consumer that has, let's say, 80%. Who do you go after, right? You may say 90%, but it's not that obvious, because what we're going to do is we're going to multiply that score with how much we expect the fraud to have been for that consumer, and that is based on the scale of the consumer. So if you have a large consumer, and that large consumer has 80% of fraud, then if you multiply that 80% with how much you expect to recover in terms of fraudulent gains, so it's kind of looking at the expectation again. What is the probability of fraud times what is the value that I'm going to be recovering from this fraud? And then finally, what may happen is that even though this person has 80% chance of being suspicious, it may be worth going after this larger guy, because when you multiply the scale of their consumption, it works out to more than 90%. 90% was happening with a small fry. So it may be 90% times 10 and 80% times 50. So you'll go with 80% times 50, right? So does that answer your question? Okay, cool, thanks.
I know Professor Sanders is a hard deadline that he put us saying at 75 minutes.
Yes, where are we?
But I think this has been bothering me a little bit.
Yes.
You're the boss, Rob.
Sorry?
You're the boss.
But it's an important question, I think, at least to clarify things in my mind. You have a formula, and you are going to sample the data that when you move bins and so on, especially in this case here, in the second case.
Mm-hmm.
So there is the mean, the estimate that you make, and there is a confidence interval around that estimate. So maybe you say, my probability is 0.5 that I estimate. They may be, that probability may vary from 20% to 70%. So if that's the case, how does that impact your results? I mean, it's much more than saying you're 7%. Because there is, among other things, false positives, meaning how often you say there's a fraud when there isn't. But how often you say there's not a fraud when there isn't? Because that adds to that might be substantial. Because the statistics has a variability, and that might be very substantial.
Right, can I?
It's quite different from saying I've got worst case.
Yeah, okay, let me actually pull up a backup slide that I have that will show you what I'm going to show you the full range, so you can look at the mean and you can get a sense for what the.
Tell me, you don't have to put up to save time.
Okay, so essentially your concern here is that I'm reporting the means, and so what would the variance look like? So in this case, I mean, if you look at the plot on the left, as you can tell, most of the readings. So what am I averaging over? Let's just first answer that. I'm averaging over multiple consumers, assuming that the attacker has the option of being any of those consumers. So I have 500 consumers, and I say that, okay, attacker can be consumer 1, how much would he gain if he was consumer 1? How much would he gain if he was consumer 2? And how much would he gain if he was consumer 500? Now, for most of these, for those options, they would gain nothing. That's why the median here is 0. And so you would see a distribution where you've got most of the readings are closer to 0, and very few of the readings are going to be further off. And so that is going to be talking about the range in terms of this particular number. Now, in terms of the optimization problem, the attacker, and there's a reason why we got to the mean. The objective function was not just about minimizing means or variances. We got to the mean because we were looking at what is the electricity bill? How do you compute that bill? And then we found an equivalence between that bill and the mean. Now, in fact, okay, so in this case, the optimization problem becomes minimizing the mean, and that's why we're talking about the means over here. And in fact, in some other work that I have not presented, what I've shown is that you can combine this min-average detector. That means you're looking at the average of consumption readings in the past. You can also combine that. You can also look at standard deviations in the past. So in this case, if you were to look at what that average attack may look like, they may be setting like multiple readings that have the same value as long as that average is a minimum average. But then the standard deviation becomes 0. So you can set a threshold in that standard deviation saying that I need to have a certain minimum standard deviation. And in that, and we can enforce the standard deviation constraints on the mean constraints. And for that, also, I have obtained the optimal attack that would circumvent that particular detector. So that I can point it to you in my thesis, but that's called the integrated ARIMA attack. And so, yeah. Yes, Al.
So a couple of questions. Both in the case of PCA and the KL divergence, is the detector trained on an individual consumer and then applied to that consumer?
Yes.
So if they're cheating all along.
Yeah. So you cannot use machine learning if you don't have a model for what is right. If they've been cheating all along, then all bets are off. Yeah.
Also, in terms of getting a collision attack and getting to my catcher's point.
Yes. Yeah.
And you want to flag a tax return that's likely to be audited. Well, you don't know the IRS's rules, but if you do a lot of tax returns and do a discriminant analysis and you know which clients are audited and which are not, then maybe you can identify effectively. If you look at more than one consumer, and maybe you can reverse engineer some of these detectors to some degree. I mean, essentially what they were claiming was a reverse engineering attack on the IRS audit rules. And therefore, they could offer to their customers that if we do your taxes, you won't get audited.
Okay. Yeah, we can talk about that. I would need to see how I can think about the reverse engineering and.
Well, no, I'm saying that if a bunch of bad people get together and.
Yeah.
Okay, I got flagged last month and this.
Yeah.
And so on. So.
Yeah.
I don't think it's practical.
Let me tell you what happens in practice. So since I did this work in industry, if you get caught with fraud, you get sued for the amount that you've committed, right? And maybe a little more than that. So there's a lawsuit, and yeah, sure. I mean, you could have collusion, but I mean, okay. I mean, I'm not sure how willing you would be to share the fact that. Like, you're putting yourself in one of these positions and you're saying that, okay, it's a criminal consortium. Okay. Okay, I have not considered criminal consortiums in my work.
I said it was in practice.
Okay, yeah. Carl.
Once there's a false positive, you just said what they would do, which is they would sue.
Not a false positive. So when there's a true positive, they would sue.
Well, how do they know whether it's true or not? They just get positive.
They would go down and investigate, and they would catch them red-handed. They would need to catch the consumer red-handed using a redundant device. So you could have one of these handheld meters that could go up to these meters and measure what is happening. You can see what the meter is giving you, and that's how you would know whether it's a true positive.
Okay, that is just Rakesh's
Okay, actually, there is a cost to a false positive. So
You have to send somebody else,
you have to send somebody out there. So that is the cost of false positive.
but it's a relatively low cost because you don't have to disrupt the consumer. You just have to send some meter person out to check it.
Right, that's right.
I know there's limited time, so maybe we should have a discussion offline, but I would say that there's actually a substantial cost to false positive. So, we keep giving the Indian example. I'm very familiar with little reasons about the tax fraud cases in India. And in a legal system that doesn't work very well and where it takes a long time, every false positive has enormous cost.
But this is not tax returns. This is
Yeah, for different applications, a false positive cost is different.
So it really depends on something that he hasn't talked about. But we just talked about what happens when a fraud, when a company says that customer has committed fraud. What's the recourse? So it's either some kind of settlement or it's some kind of lawsuit. If it's a lawsuit, then
no. They go out and check it.
Yeah, they go out and check it. So you go out and check the meter, and if you see fraud, then you sue the guy. If you don't see fraud, then you have lost the cost of sending that person out to check it.
No, I think the cost is associated with you being wrong, either in negative or in positive. And whether it's large or not depends on the problem.
Yes, it depends on the problem.
I think we should move on.
Okay. So in the context of rooftop solar, just coming back to that, we showed that we could use correlation models. So going back to the data framework, since solar power generation, as I said, you have these spatial relationships. You have your house and your own neighbor's house, and you're looking at their generation. And you can use these correlation models to mitigate that fraud by 77%. And just to kind of give you a flavor for what that correlation looks like, here's a correlation matrix for 300 different prosumers in Australia. And what you can see with the color axis is that their correlation coefficients are very high. So they're very highly correlated with each other. And so you can use that fact to leverage correlation models for detection. So now let's move on to the final part of the talk. And this entire chapter is new for the committee. So this whole part was done after my prelim. So here the billion-dollar problem is that cyber attacks can induce these power outages, and it costs billions of dollars to the economy. And the problem exists because critical infrastructure controls are becoming increasingly connected to operational technology networks. Many of these controls used to be air-gapped, but now they're no longer air-gapped. So malware like crash override, which I talked about at the top of the talk, can enter these control systems and cause outages. So here the research objective is to understand how an attacker may gain access to generation controls. And then we're going to evaluate the minimum effort for an attacker to be successful. And then finally, we're going to identify approaches to mitigate these attacks. The power grid is already very resilient. Professor Sarah will agree with me. So there are plenty of resilience mechanisms. And now I'm just going to talk about one mechanism that's called primary frequency response. So what I'm showing you here is an illustration of a power grid model. It's a standard model, IEEE model. It has 10 generators that have been circled, and it has 39 buses that have been labeled. And this illustration comes from the Power World simulator. Under normal circumstances, these 10 generators would be generating varying amounts relative to their generation capacity. So the vertical axis is relative to their capacity. And that amount depends on their cost factors. You've got different dispatch scenarios. And so different generators will be generating different amounts. So now let's look at a contingency. In this contingency, I'm going to call this generator generator 1, and I'm going to disconnect that generator. So as a consequence, that generator's output goes down to 0. But what you see is that these other generators are automatically increasing their power production in response to that generator failing. And the mechanism that accomplishes that is called primary frequency response. There are other mechanisms beyond primary frequency response, but let's just focus on this for now. And what you can see here is that these arrows in the diagram show the power flows from the other generators into this bus 39 where the generator was disconnected. So the other generators are compensating for the power that was lost in that bus 39. So why is it called frequency response? So what happens is that when I disconnect that generator, the grid frequency drops. The nominal value is 60 hertz, but the frequency drops to below 60 hertz because the generator was disconnected. What primary frequency response does, or tries to do, is it tries to restore the frequency above a safety threshold. So this safety threshold is set by NERC, the North American Electric Reliability Council. And primary frequency response has one job. It just needs to restore the frequency above that threshold within 30 seconds, because that's how long it takes for what's called secondary frequency response to kick in, or AGC. So let's say in this scenario, it was successful, and so this primary frequency response succeeded. After 30 seconds, secondary frequency response kicks in, and that's also called automatic generation control. I'm going to refer to that as AGC. And now what AGC would do at this point is that it's slightly below 60 hertz. AGC would just bring it back up to exactly 60 hertz. Well, nothing is ever exact, but close enough to 60 hertz. And then in that case, the system is stabilized. Now let's look at the failure scenarios. If primary frequency response fails to restore the frequency within 30 seconds, then you would have what's called under-frequency load shedding. And that is illustrated by the second curve, the red curve over here. The frequency drops below that. And the reason for that is that AGC would kick in after 30 seconds, but it's already too late. The relays are programmed to open when they see this drop in frequency. Now, there are other things that can happen. Like AGC could fail to maintain that frequency, and if that fails, then you could still have under-frequency load shedding. And that is a problem that has been discussed in related work. In fact, there are some people here in the audience who've done that related work. So Professor Iyer, Professor Kalbachik. So Rui Tan was the lead author on that work, where he's looking at the failure of AGC. What people have not looked at, and this is what we are the first to look at, is the failure of primary frequency response. And why have people not looked at it? Because so far it has never failed. But our work is really looking at that failure from a malicious standpoint. So a cyber attack is going to cause that to fail. And for this study, we've used the Power World simulator because these changes in frequency require what's called transient analysis, and Power World has that capability. So we've come up with a new threat. This is an attack on resilience, so attack on the primary frequency response system. Here, the attacker could be a nation-state attacker, it could be a terror group, or it could even be an energy company like Enron. So in 2001, Enron artificially created power outages in order to drive up prices and gain profit. So that is also very much part of the attack model. The goal of the attacker is to create an outage, but another important part of this goal is that the attacker wants to be as inconspicuous as he can be. They want to try and get away from this or make it look like the attack happened for non-malicious causes. And so I'm going to quantify what is the minimum effort that an attacker would need to take so that they can potentially circumvent detection. Yes. Yes.
Where does the cyber here come from?
Yeah, so right now,
These are physical systems, right? And the resilience in this particular space is physical.
yes. I'm going to bring in cyber in the next slide. So just give me one slide and then you will know.
Well, Varun, there's two primary frequency responses that you could talk about. One is the inertia.
Okay.
So that's what causes the steep drop. But then the governors detect that there's a frequency error, and so they are supposed to recover. So you're talking mainly about governor response, right?
Yeah, in fact, I'm talking about attackers on governor response. The attacks. Yeah, I'm talking about attacks on governor controls. Yeah. So the attack is going to, so there are controls, there are control systems that make this happen, and we're going to attack those control systems in the next slide. So that's where the cyber aspect comes in. It's happening in the SCADA space, correct, exactly. So the attacker's capability is that they can infiltrate the OT network, so that is the SCADA space, and they can modify this parameter Pmax. So let's talk about that parameter. So as I had in the previous deck, I showed the case where that frequency kind of stabilizes to a safe value. And that happens because, again, as I said earlier, these other 9 generators, they increase their production to compensate for the lost generation in generation 1. They are able to do that because there's a parameter called Pmax in that control system that essentially restricts how much they can generate. So this is a governor control parameter.
I also want to sort of comment, this is a physical attack, right?
It's a cyber attack on a physical system.
Goes down, okay, so
This could be caused by physical means.
by physical means, but then basically.
No, by cyber means. I said it wrong.
we're going to cause so it's a cyber attack that is going to make multiple things happen. So
The loss on generator 1 is not a cyber.
that need not be, yeah, correct. Oh, thank you so much. Yes, that does not need to be a cyber attack. Yeah. So I haven't yet gotten to the cyber attack yet.
Basically, that somebody uses that kind of physical failure.
Yes, you uses that failure to
actually start to attack the cyber.
correct. So let's talk about the attack.
It's better, I think, to be able to go to that generator and push a button or a series of buttons, because these are massive things. It's not easy. It's much easier to get on the internet and be able to go and do something like that.
We're going to do it from the internet. Let me just make a little more progress. You're asking me questions that I'm very happy with because I'm going to answer them. Yes, correct, exactly. Thank you. That's really what the attack does. So what the attack is going to do is it's going to go into that control system and then reset that upper limit. So in this case, Pmax is reduced to 90%. And as a consequence of that, these other 9 generators were not able to compensate for the loss of generator 1. And so you see this other curve here. This frequency drops below the safe threshold. And this is an outage scenario. So what the attacker is doing is they're changing just this one control parameter. And I'll talk about how right now. Okay. So let's look at the attack steps. So typically in these attacks, you have 2 phases. There's a preparation phase. Like in the case of crash override, they estimate that the preparation phase happened over a year. So it could be several months. And then there's the execution phase, and that could happen in a moment. Okay? So let's talk about those phases. The first step is for an attacker to gain access to the OT network. So Ravi, here's the attacker. The attacker is on the internet somewhere, and they need to gain access to the OT network. And the issue with that, so OT is operational technology, IT is information technology. And the challenge here is that the attacker needs to go through several security mechanisms that are in place. They need to circumvent a perimeter firewall around the organization. So the organization starts with this perimeter. This is the generator company. They need to get into the IT network. And then from the IT network, there should be some access control layers that they need to circumvent again at the OT network. So I'm assuming that they do exactly what they did with crash override. The first step is you circumvent that perimeter firewall through social engineering, or as Pete likes to put it simply, email. You just send emails, and then somebody in the IT network clicks on the email, and now they've got the malware downloaded. And then the next step is called lateral movement. So the malware starts to acquire credentials while it's sitting in the IT network that allow it to gain access to the OT network. So once you've gained access to the OT network, the malware will the attacker will install the malware that will reduce Pmax. And that is accessible directly from the OT network because Pmax is a generator controller that's connected to the OT network. The final step is that either the attacker could cause that generator 1 to fail, or they could wait for the generator to fail for non-malicious reasons. So there's 2 ways by which that first generator that you were talking about could be made to fail. But the real point here is that if I just disconnected that generator, nothing is going to happen to my grid. That's because the other generators will compensate. So the attack is in trying to look at to limit the capability of the other generators to compensate. So now let's look at the minimum effort for an attacker to cause an outage. So we're looking at this from 2 attack parameters. One attack parameter is what is the minimum number of generators that the attacker needs to compromise? And what is the level to which that Pmax parameter needs to be reduced? So let's take an example. So this was the same example that I had in the previous slide. The attacker reduces the Pmax value to 90% for 9 generators. And this whole curve was obtained from that particular power grid model that I'd shown you earlier. And this is an outage scenario, because if you reduce the Pmax value to 90%, you need to compromise at least 9 generators. If you compromise 8 generators and you reduce Pmax to 90%, you won't have an outage. The frequency will not drop below the threshold. So let's look at a more interesting example where let's say Pmax was reduced to 55%, but only for 5 generators. So in this case, we're allowing these 4 generators to compensate, but we're going to be capping the maximum for these other 5 generators. This is also an outage scenario. So from the attacker's perspective, they can think about what is the least they can do in terms of, so if, for example, the attacker was only capable of compromising 6 generators, then the attacker would need to reduce Pmax below 80%, because if they were compromising 6 generators and they'd only reduced it to 90%, then they would not have an attack. So this is kind of looking at the attacker's resources in one case, and the other case is looking at how obvious the attack is going to be. If you reduce Pmax too dramatically, then that may become obvious. And so the general trend is one you may expect, is that when the attack on each generator becomes more severe, so I'm going to reduce Pmax to a lower amount, then you need to compromise fewer generators. Carl?
How is Pmax chosen by the utility, and do they ever change it?
That's an excellent question. In fact, that is exactly what's going to come into play when I talk about prevention. Very rarely they need to change that value, and that value is really set to ensure that in some rare cases, like let's look right here. What you can see with these Gen 2, Gen 4, Gen 7, and 8 is that their generation is exceeding 100%, which does not, you may think that how is that even possible? But it's possible for a very short period of time. So that Pmax value, when there's a contingency, that value can be increased beyond the generator's reading, so that for a short period of time, the generator is operating beyond its rated capability. If the generator were operating beyond its rated capability all the time, then the generator would get damaged. So that rated potential is really talking about, what's the safe values that they're operating within. Okay, so that is really when that value needs to be changed. But it's only in the past 5 to 10 years that control system has become connected to OT networks. Before that, somebody had to go in person and turn a knob or push a button, as Ravi was saying, to make that happen. So it really was not. It's probably something that it could still be air gapped. But this is the ugly consequence of smart grids, right? We're connecting everything, and that's what can happen.
But there is the other option of just getting at the AGC, which is easy.
Yeah.
And lowering the output until you get the tripping from under frequency.
Right, and the reason I've not looked at that is just because related work has looked at that. So there's plenty of work out there that's looked at AGC.
That would be just as good as this.
Yes, it would be just as good. Yeah, but
It's much easier, probably.
yeah, and it's much easier. I'm glad that you mentioned that, and it's also something that Clara was asking me earlier. It's easier because in this case, the attacker needs the frequency to drop before 30 seconds. So there is a timing requirement. If the frequency does not drop below the threshold, then AGC will kick in, and then AGC will recover everything. So yes, so this is a harder attack, but yeah.
If you're into the OT, you may as well go for the AGC.
Right.
And change that one. So
Right.
That's every 2 seconds.
So does that mean that nobody would ever do this attack, or is there a way to protect against that other attack?
There's related work on protecting AGC. So there's plenty of work that talks about how you would detect attacks on AGC. In fact, again, as I said, Professor Iyer is a co-author on one of those works. Yeah.
But Pete was making the argument that this isn't very interesting because you'd always do the other. But if somebody protected against the other, then this one becomes important. That's what I'm trying.
Yes, I mean, you want to protect against both. So related work is protected against one and protecting against the other. That.
Especially if you have a malware.
Yeah.
The malware basically sits in there
Yeah.
and fall.
Right.
And it can go in very fine-grained ether
Yes. Yes.
to change the.
Right. Exactly.
And actually, the Pmax is a parameter in the AGC, so
You can do the same thing.
the AGC and
Right.
either set the actual output below or change the Pmax. You can do either one.
Right.
You can see how this might happen, so that this thing becomes available now for people to run in short times and over capacity. And so someone could think that's what some operator was trying to do that. And in fact, it might be part of an attack that's got many components and is trying to appear like an ordinary failure.
Yeah. I didn't think about that. That's a really nice point. Yeah. So yeah, that could be part of the attack model.
I
I have about 5 minutes or so. Yeah. Okay.
I have a question, but I'll ask after the 75 minutes.
Okay. Sure. Okay. Yeah. Sure. We can talk about that. Okay. So now let's talk about detection. Okay. So we are trying to detect that compromise of that Pmax value, and the challenge for the detector, and this was the same that happened with Stuxnet, was that once the attacker is in the OT network, they can compromise your human-machine interface to make it look like everything is normal. So that is exactly what happened with Stuxnet. They'd gotten into these uranium centrifuges. They were spinning out of control, but their screens were saying everything is normal. So the only real way around this is you need to have some redundant out-of-band measurements that can help validate your HMI readings and check whether this is working. So like Professor Sauer was suggesting that you could easily install an RPM meter, so that's also called a tachometer, to check whether the frequency has dropped. And if it has dropped, then you know that there's an attack in your system, and I'll soon talk about how you would respond to that. But now let's go back to some data-driven stuff. Now let's look at a special case of wind power generator compromise. So now here the attacker is compromising a wind power generator. And so what the defender can do is that the defender can use wind speed estimates. They could come from a local weather station to estimate wind power output and check for anomalies in wind power output. So that can be modeled with data. So let's show you some data. So this data is taken from measurements from a 2-megawatt wind turbine in France. This is called a power curve. It's between wind speed and wind power. And here again, wind power, instead of showing it to you in terms of megawatts, I'm showing it to you in terms of percentage of the rated capacity. So what you see in this plot is that the wind turbine is only going to generate its rated capacity beyond, in this case, 14 meters per second. And that's called the rated speed for this wind turbine. So you need strong wind in order for the wind turbine to produce more. Now let's just look at that region, that rated speed region, when wind speed is greater than 14 meters per second. And let's plot a conditional probability distribution. So this is the wind power given that my wind speed is greater than 14 meters per second. So wind power on the horizontal axis, and this is the relative frequency. And so when the wind speed is greater than 14 meters per second, you can see that the band that wind power is going to be generating is very narrow. So you could say that Pmax may have been compromised if the generator is generating less than, in this particular chart, 92%, given that my wind speed value is so much. So I got my wind speed values out of band, and then I have some expectation for what my wind power output is going to be. And if the actual wind power output is less than what I expect based on data, then we can say that perhaps Pmax has been compromised. Because the only cases where the wind power would be less than this 92 threshold are very few. They're less than 2%. So your false positive rate would be 2%. So let's talk about the detector threshold. So if I were to set the detector here, then it will detect any changes to Pmax less than 92%. And as I mentioned in my earlier work, we're talking about reducing Pmax to 80%, 90%, 70%. And if you reduce it to like 70%, then it will be easily detected by this detector, right? And the way I got that 92% was by training it on a certain amount of data and ensuring that the false positives on that training set were low. And then I also had a holdout set to kind of check whether the false positive rate in that holdout set was similar to what I'd see in the training set. And yeah, it was actually less than what I'd see in the training set. So now let's summarize the work on cyber resilience. So in analyzing the attack, we showed that primary frequency response can be compromised to induce these outages by compromising that parameter Pmax. And we showed that you can control Pmax if you get access to the OT network, and we also described how one could get access to how a cyber attacker could get access to the OT network. And we also quantified what would be the minimum effort for the attacker, because Pmax needs to be compromised for a sufficient number of generators by sufficient amount in order to cause that under-frequency scenario. And we showed that the attacker could hide by spoofing the HMI interface. In terms of mitigation, we showed that you require some redundant out-of-band measurement to validate your HMI readings. In the case of wind generation, we showed that out-of-band measurements of wind speed data can be used as a proxy for wind power generation because there's a very strong relationship between wind speed and wind power, so that's the data-driven part. What we didn't really talk about is prevention and response. So in this case, prevention, these are both kind of generic steps that you can take for any system. So prevention here, the idea is better cyber hygiene. and that encompasses better training against social engineering attacks, so people don't click random links in their email. And then you could also have two-factor authentication for critical controls, right? If you, especially something like PMAX, that you're not going to change that often, then maybe you could design a system that if you did want to change that, then you have, well, I think you should have two-factor authentication for everything regardless. But yeah, I mean, especially for those controls, it would be good to have that. And the response is, again, kind of generic. If there's a fault in one part of your system, you isolate that system and from the rest of the network, and then you reset it to the safe setting. So in conclusion, my PhD thesis work addresses the good, the bad, and the ugly consequences of smart grids. In terms of resource utilization, we showed how we can reduce the prediction uncertainty associated with wind power. We didn't really talk about the consumption part because I talked about that in my prelim. In the case of fraud detection, we showed that we can dramatically mitigate fraud for both solar and consumption fraud. And in terms of the ugly consequence of smart grids, cyber attacks, we discovered a new attack, and we showed how to empirically detect that attack. And this attack is on generation controls, and it can cause power outages. So through those contributions, we demonstrated that empirical models of generation and consumption, constructed using machine learning and statistical methods, improve resource utilization, fraud detection, and cyber resilience in smart grids. So here's a list of the publications that are in my PhD dissertation. I just want to point out that all the conference papers here are all actual publications ranging from 6 to 15 pages. None of the conference papers here are abstracts as they are in some other communities outside of computer science. I really want to thank all my research collaborators. All their names are listed as co-authors on these papers, and many of my collaborators are here in this room. So thank you. And the reason why I've been using the word we throughout this whole talk is because they were very much involved in all of this work, and it wouldn't have gotten done without their support. And I also want to thank my funding agencies. So there's the Department of Energy and the Department of Homeland Security, the Siebel Energy Institute, IBM Research, and A-Star for supporting my work. And then I want to thank the CSL and ECE staff, most of all Jenny Applequist, who reviewed all of most of these papers and made them look a lot better. And I want to thank my friends and colleagues here in CSL, especially the Perform group, who helped me prepare, and Depend group, and who helped me prepare for not only this talk, but also helped me improve my research throughout. And I want to thank my ballroom dance team, many of whom are here, because they helped ensure that I had fun outside of research. Then I want to thank my committee members for their guidance on my work. I want to thank my friends and family for their support. And most of all, I want to thank my advisor, Professor Bill Sanders, who's always believed in me, believed in my ideas, and trusted me to represent him and the university at national and international forums. That is the end of my talk. Thank you. If the floor was wooden, then I'm sure we may have been able to oblige.